My name is Pat Skinner. I'm a first-year PhD student at Texas Tech University, the Wind Science and Engineering Group. And I'm going to talk to you about stick nets today. This is our primary surface observing system, and it was actually the primary surface observing system for Project Vortex 2 last year. We have 24 of these stations that we attempt to deploy out in front of supercells, and we also do it in hurricanes, but gather readings, certainly in the forward flank, the rear flank downdraft, anywhere we wouldn't really want to send vehicles in a storm. So it's all mounted on a heavy-duty tripod, a surveyor tripod. These have been wind tunnel tested to withstand up to about 140 mile-an-hour winds, at least when we have an earth screw in it. Standard RM Young prop anemometer on top, and then this is a flex gate compass so that we can back out the wind direction. When we put these down, we don't really have time to align them to true north, so with this, we can actually just calculate the wind direction without actually worrying which direction they're facing. We have an aspirated temperature relative humidity sensor, also a barometer in there, which goes into our data acquisition box here. And then we have a GPS unit here, which lets us know where it is. And anyways, in here we have a compact field point module from National Instruments, which logs all of the data that we collect. It actually is all stored on a SanDisk card, a 1 gigabyte card, so just like you have in your digital camera. We can download it off of the card. We also have Ethernet adapter on the side back here, so we can plug this in our trailers and actually download the data while we're en route back from the storm, so we can download up to 12 of these at the same time. And we have a second design of stick nets as well. This is does the exact same thing as the last probe, except we have an all-in-one Vasala sensor at the top. So this, you can see the prongs at the top, that is a sonic anemometer, so you get wind speed and wind direction from that. Also temperature, relative humidity, and barometric pressure. It also has a pressure plate at the top that senses rainfall rate and also hail size. So both of these have worked equally well in the project or field for us so far. We've been fortunate. The only probe we've lost thus far was in a hurricane, and it was due to a truck backing into the tripod, and it knocked one of the legs off. So far they've proved to be really rugged, and we're grateful for that.
Okay, we're going to go over and take a look at the trailer.
Sounds good. So we're back and we're now looking into one of the trailers we use to transport our stick nets. As you see, we can line them up here just along the sides, and we fit 12 per trailer. We have 2 trailers, so we have 24 probes. We're building a 25th probe as a display unit. And what we do when we deploy in Vortex 2 and other projects is we have about half the probes, or we take 5 probes out of each trailer and fit them onto a custom fitted rack on a pickup truck that allows for quicker deployment and also more maneuverability of the vehicle. So those 2 pickup trucks that aren't fettered by the trailer can actually get up close to the tornado and sort of wait to the last minute to deploy. While these trailers will then deploy from north to south to make sure they get out of the storm before it starts to impinge on them, and drop off kind of a broad scale array. The pickup trucks will then fill that in once we have a better feel for where the mesocyclone is going to pass. So ideally what we want to do is have the mesocyclone pass right through the middle of our fine scale array. And we've had some pretty good success with that in Vortex 2. I can't remember the exact number of deployments, but we would send it out in 2 strips generally, so we get some sort of time evolution for it. And certainly on days like the Lagrange day with the tornado, we had the tornado, as it was roping out, passed within a couple hundred meters of one of the stick nets. So we got some excellent data on it in Vortex 2. Unfortunately, there weren't too many cases, but we certainly made the most of what was given to us.
So on average, how many of these do you have out at once?
Ideally, we have them all. So when about an hour before the storm sort of hits point A, we call it, Dr. Chris Weiss, who's running the project or coordinating it, will give the go-ahead. We'll start dropping off the coarse scale array. About a half hour after that, we'll start dropping off the fine scale array, and we'll do it in 2 strips of 12. And then as the storm is starting to, the updraft is moving over the fine scale array with the first 12 probe array there, we're hoping that we have all 24 probes down and that we get evolutionary data as it passes over the first array and then onto the second one, which is generally to the east.
Yeah, and these are in addition to the mobile mesonet you have as well.
That's correct. Texas Tech, we have 2 currently working mobile mesonets. We have the capability to do those up to 5, and those are actually on loan to NSSL right now. So they're currently modifying and adding it to their fleet of, I believe, 7 mobile mesonet probes. So all told, between that and then the probes that CSWR uses and their mobile mesonets, there is obviously a lot of capability for surface observing in Vortex. Okay, so we're now looking at one of Texas Tech's 2 Ka band mobile radars. One actually did go out in Vortex 2 last spring, did sample the Lagrange tornado, unfortunately from a little bit further away than we would have liked. So we're really anxious to get this and its companion radar out again this year and see what they can see. We've made some improvements to some of the signal processing as well, so our resolution has increased even more than what it was. These were designed and custom built by Jerry Gwines, who's a radar engineer here at Tech. And what he did was he utilized the Ka band as well as a traveling wave tube, which is unique to any other mobile radar in the world right now. And it really allows us a lot of flexibility and a lot of freedom in how we shape the pulse and what we actually send out of the antenna. And it gives us the ability to become a lot more sensitive, and in our signal processing actually kind of artificially enhance the resolution. So it's a resolution right now we can actually deal with nearly 10 meters. Hopefully with better processing in the future we can actually get it down under 10 meter resolution, at least from beam to beam, or gate to gate, excuse me. It's very helpful that way. It also makes it a little bit more sensitive to Doppler radar, this ability to chirp or shape the radar pulse that you send out of the radar. So it's really a one-of-a-kind radar in the world. Actually, it's two-of-a-kind because there are two of them. So we're very excited about its capability, and we'd love to get it out there and see what it can do. If you look inside here, we're now looking at just a navigator position here, and it's just this regular laptop mounted there. That's where we use to look at broad scale radar, really position ourselves, use DeLorme, just get our positioning mapping, but it also has a program that allows us to level it with the four platforms here. So it shows up just like a cockpit screen in a flight simulator, and you push down using the gearbox in the middle there, all four of the hydraulic legs, until you get it to a point where it's level, so you obviously then know which direction you're shooting the beam. And the beam is all controlled from a Linux box back here that Jerry is typically working at, and he has got many custom programs in there that allow him to scan pretty much whichever way he wants on the fly. He can just enter in angles, and we can change sectors. We can switch from RHI to PPI and do it with little or no time wasted. So it's certainly got a lot of flexibility in the way we scan, hardly ever break scanning periods, and we're generally always level, so we know where we're scanning. So there's not a lot of missing data here. It's been very reliable so far. And moving back, we have the generator. We have a heavy-duty air conditioning system back there. The heat generated by the energy as it's ramped up through the traveling wave tube is just below the threshold that you need to have a liquid cooling system. So we have a very heavy-duty air conditioning system. It gets very cold in the cab. Some of it's routed in there when we're scanning. And then you can see back here we have the radome to protect against hail and wind. And if you point in there, you can see the pedestal and the antenna. And one nice thing, the dish is actually not that large compared to others, but because we have the ability to shape our own pulse and we're operating at a Ka wavelength, which is a very small wavelength, we're actually able to get a very low beam width comparable to other larger radars using a small dish. So even though the dish is small, we're not losing anything in the way of resolution by using it.